Okay, let's knock out our fourth page, hopefully to highlight a last super important property of integration, and then we'll sort of use these things real fast, and then that's about it. So, same game. You've got a function f, you've got a function g, and the third function is h. But what the third function is what you get when you multiply half of x and 2x. aka it's just f times g. Half of 2 is just 1, so those kind of cancel out, and x times x gets us x squared. So first, we want to integrate this half of x from 0 to 3. So this red little rectangle would be 3 long. It'd be 3 halves high. So half of 3 times 3 halves should get you 9 quarters. The g function should work out a little prettier without fractions, but you want to integrate this function. This guy winds up being 3 wide, 6 tall. Half of 6 times 3 should be half, that should just be 9. Or it's really just 4 times bigger than this one, because 2 is 4 times bigger than a half. And then I ask you to do two weird things on the bottom. The one thing I ask you to do on the bottom is to just take your two answers for f and g and just multiply the two answers. So 9 quarters times 9 over 1 is 81 fourths, or basically 20.25. So I ask you to just take your two answers and multiply them. And then the other thing I ask you to do is basically multiply them first and then try to integrate it. So if we multiply them first, f of x times g of x just is telling you to do x squared. So I just want to find this area from 0 to 3. That's it. Now it's a curve, so we actually haven't learned how to do this yet. It's not a circle. We could kind of figure it out if it was a circle or a semicircle or something like that, but it's not. So let's talk about this little curve. If we look at x squared from 0 to 3, and we made a little bit better of a graph, it looks sort of like this. You want a horrible estimate for this area? Here you go. This one rectangle is going to be the area of that region. I want to find the area of just this red stuff. And I know that red stuff is actually the actual area. I just want to figure out if that red stuff has an area of 20.25, and I say there's no way it does. Because this big giant rectangle that covers all this stuff that we don't want to include is 3 for the base and 9 for the height. So that green rectangle is 27. That's its area, is 27. And this little curve that cuts through it, the area we're actually talking about, is maybe half of that. In fact, it's got to be less than half of it, because a perfect line would give you half of this. This is less than half of 27. Now, this maybe feels like not that important of a concept, even though we can't do this perfectly. That seems like the bigger, more important idea. How do we do this exactly? This does get us a one super other important property of integrals. That if you try to integrate a function f times a function g from a to b, it is not the same thing as doing them one at a time. Not. So if the functions are multiplied, you cannot split them up and do it one at a time. If they are added or subtracted, it is okay for you to just split them up and do them one at a time. It's totally fine. That's it. That's the big, super important thing. Hey, guess what? That property we just sort of talked about, or I guess it's more of a non-property. It's more about something you can't do, but it's also true for antiderivatives. You cannot split up functions. You cannot just do them one at a time. Do the first multiplier with the second factor. You can't do that. So, surprise, surprise, the thing you can't do for antiderivatives, you also can't do for these weird squiggly looking expression things that we're calling integrals when there are numbers in the bottom and top. That's about it.